So, today we will be discussing some problems and essentially this is going to be a review lecture and we will solve some exercises which I think is going to be beneficial for you. Okay, let us start with we have defined limit. First we did function and then we introduced the concept of limit. What we have seen is that suppose we have x square plus x minus 12 divided by x minus 3, this may not be equal to x plus 4. The numerator is x minus 3 into x plus 4, but at x equal to 3, this denominator is 0. So, this is not a well defined term, but this is equal to x plus 4 if x is not equal to 3, that is for sure, and hence we can define this limit x goes to 3 . So, now limit x goes to 3 means x is not equal to 3. In a very small neighborhood of 3 we are considering our x. So, in that case this is going to be limit x goes to 3 x plus 4 which is equal to 7. So, this is the concept of limit we have defined. So, similarly another example we can take, this is example 1, example 2 we can take limit x goes to 7 square root of x plus 2 minus 3 by x minus 7. So, now how we are going to find the limit here? So, what we do is that this we can write x goes to 7 square root of x plus 2 minus 3 into square root of x plus 2 plus 3 divided by x minus 7 into square root of x plus 2 plus 3. Now, numerator is in the form of a minus b into a plus b. So, this is x plus 2 minus 3 square is 9. Now, here it is x minus of 7 in the numerator, x minus 7 is in the denominator. So, this is limit x goes to 7 1 over square root of x plus 2 plus 3. This is equal to, now there is no problem 0 or anything. So, this is 1 over square root of 9 plus 3, this is equal to 1 over 6. So, there are various other ways one can compute the limit. One of the very important technique to find the limit what we have seen is squeeze theorem or sandwich theorem. So, what does it say? It says that essentially if h of x is lesser equal to f of x is lesser equal to g of x, and this goes to a limit alpha as a goes to x goes to a, and this goes to the same limit of alpha as x goes to a, then f has no other choice, but this has to go to alpha as x goes to a. This is what is the sandwich theorem. So, let us see one application of this theorem. So, let us try to find out limit x goes to 0 square root of x e to the power sine pi by x. Now, pi by x, sine pi by x, x goes to 0, we cannot determine the limiting value. However, if we look at this, then we are always considering the positive square root. So, this is sine pi over x. So, when as x goes to 0, this sine pi over x is always wherever the x is, sine pi over x is always bounded by 1. So, this is going to be less or equal to square root of x times of e, and which is definitely greater or equal to 0. Now, this side, this goes to 0 and this is 0. So, this we can write it as this goes to 0. Square root of x e to the power sine pi by x is essentially dominated by some constant times square root of x, and that is going to determine the limit. Okay. So, now we have come across with a situation that the limit may not exist, but the right hand and left hand limit may exist. So, one of the example which we can now look at, let us look at pi by 2 plus a bracket of cos x. Now, if cos x graph, this is going to be this. Now, if we are coming from this side, now cos x is going to be negative. So, therefore, the bracket of cos x, bracket is the greatest integer function. So, this is going to be negative 1. So, therefore, this is going to be minus of 1. Now, limit x goes to pi by 2 minus bracket of cos x, if we are looking at this, which means if we are travelling from this side, cos is positive, therefore, which is less than 1 in the neighborhood of pi by 2. Therefore, the bracket of cos x is going to be 0. So, this is 0. So, therefore, the limit of does not exist. However, the left hand and right hand limit exist. Now, we say that if the limit exists, it may also happen that the limit of a function exists, but it may not be equal to the functional value at that point. If it matches with the functional value at that point, then we say that f is continuous. So, one example we can see that define f of x, this is equal to sin x if x is less than pi by 4, and cos x if x is greater or equal to pi by 4. Then obviously, what you can see is that, so this is the function, this is pi by 4, this is 1 by root 2. So, this goes like this, and then this is 1 by root 2, and then basically this comes down to this, and this is pi by 2. This is cos x, and on this side this is sin x. This is the entire function on the real line. So, this is 1. So, this is, however, this is a continuous function as f continuous, because outside from pi by 4, x less than pi by 4, it is sin x, which is a continuous function, x greater than pi by 4, which is cos x, again a continuous function. So, we are only interested in finding the behavior at pi by 4. So, limit x goes to pi by 4 of f of x. This is equal to, if on the left hand side, if I am going, then I am going to get, this is sin pi by 4 is 1 by root 2, which is also equal to limit x goes to pi by 4 plus of f of x, because that is going to be cos x and that is also 1 by root 2. And therefore, the limit exists and is equal to 1 by root 2, and it is given that at pi by 4 it is taking the value 1 over root 2. So, this is a continuous function, and sometimes we encounter the function which is given in the form of, let us say, f of x is equal to a x plus b if x is greater than 0 and is equal to x square if x is lesser equal to 0. So, the question may occur that for what value of a and b the function is going to be continuous. Now, suppose for example, what we see is that if a is equal to 0 and b is equal to 1, on the positive side it is going to be constant function 1, and on the negative side this is going to be x square. So, there is a discontinuity at x is equal to 0. So, now for us the problem is to find out all the values of a and b for which f is a continuous function on R. So, now as you can see that if x is greater than 0, then this is a linear map. So, which is continuous, and x is lesser equal to 0, this is x square, which is again a continuous function. So, we are only interested at x is equal to 0. So, now limit x goes to 0 plus, if I say, of f of x, then this is going to be b, and limit x goes to 0 minus of f of x, this is going to be equal to 0. In order to have f to be continuous at 0, so to have f continuous at 0, we must have b is equal to 0. And as you can see, what it says that it does not matter what value of a we take, as long as our b is 0, f is continuous. So, f continuous if a belongs to R and b is equal to 0. That is what various question we are asked to find out the values of a and b for which f is continuous. Then there can be one of the very important feature of the continuous function on an interval, when it is defined on an interval and continuous, then basically if there are 2 points where f is taking values, then any value between these two, there will be a x such that f of x is going to attain that value. That is what is intermediate value theorem. So, using that, so we can say that in some algebraic equations, whether they can have a root or not. This may not say whether we have precisely what x is going to be the root of the equation, but at least we can say qualitatively that there is a root between in this interval, in some particular interval. There will be several type of questions, we have done it in the lectures. So, today let us look at, so suppose I am worried about, does ln x, which is equal to e to the power minus of x, has a root in or on one 2. So, for that let us look at f of x is equal to ln x minus e to the power minus of x. Surely, if I take the closed interval 1 2, then f is continuous. So, we have satisfied the condition of the theorem of intermediate value property. So, now let us look at f of 1. This is equal to ln 1 is 0 minus e to the power minus of 1, which is negative. Now, let us look at f of 2, which is equal to ln 2 minus e to the power minus of 2. Now, ln 2 is approximately 0.69. Now, what about 1 by e square? E is approximately equal to 2.7. One can show that this is actually is what one can show that this is less than equal to 1.15 square, because E is certainly bigger than 1.5. So, this is definitely lesser equal to 1 by, this is 2.25. So, which is less than 2, which is equal to 0.5. So, now ln 2 is 0.69, approximately 0.69 is greater than 0.6, and e to the power minus 2 is less than 0.5. So, this is going to be bigger than 0. Okay. So, now f of 1 is negative and f of 2 is positive. So, there exists an x naught belongs to 1 and 2 such that f of x naught is equal to 0. And another important feature of the continuous function is that if a function is a b to r continuous, then obviously f is from a b to c d, some closed interval, and that is because the f, a continuous function on a closed and bounded interval, is going to attain its maximum and minimum. So, we, in order to find where it does attain the maximum or minimum, we need the help of differential calculus. So, which we will see at a later stage. So, now the derivative, there can be various things. We have defined the differentiation, then we have defined the algebra of the derivative. If f and g are differentiable, then f plus g is differentiable, f g is differentiable, so on and so forth, which you know. One of the things which I want to discuss today is also that it may not be true that if f g is differentiable, then f and g both are necessarily differentiable, which so may not be true. So, for example, you take f of x is equal to g of x, which is equal to mod x. Therefore, we know that neither f nor g are differentiable at x equal to 0. Now, if you take f of x into g of x, then this becomes mod of x square, and this mod of x square is differentiable, because as you can see that limit of h goes to 0, this becomes divided by h. Now, it does not depend on the sign of this. So, this is going to be 0. So, both or one of them may not be differentiable, but the product can be differentiable. And the trivial example, you can say that you take any non-differentiable function and you take g to be 0 function, then the product is going to be 0 function, and that is going to be differentiable. So, the converse is not true. And also, if f is differentiable, then f prime is a function. But we really cannot say that f prime is continuous or f prime is differentiable. So, obviously, that is not going to be true. So, we have seen various examples towards this. One need to be very careful while calculating the derivative of a function. This is a function where we need to apply the product rule as well as the composition of that. So, what we know is that this is the first one. If I take, then this is 1 by square root of 2 x. I simply keep 1 over x square, then I keep the first one and take the derivative of the second. So, similarly, if you have f of x is equal to 1 over sine square root of x wherever it is defined, that sine square root of x is not equal to 0, then this is differentiable. Then what you are going to get, that this is sine square root of x square, then minus of 1 into this is cos square root of x, then square root of x derivative is 1 by 2 square root of x. This is the chain rule. So, be careful about while defining the derivative when it comes up with the composition of map. Then as an application of that, we have sketched the curve, and then what we do is once we there we need to be really careful about finding out the asymptote and as well as where it is attained, the absolute maximum and minimum, uh, and then the bending of the curve, concave up or concave down. For that we need to go to the second derivative. So, and then if it is bending from concave up to concave down at one point, then we say that that point is a point of inflection, and so on and so forth, and various optimization problem. And also we have done the implicit differentiation. So, in the next lecture we will do some problem based on implicit differentiation as well as integration and infinite series. Thank you.